host, the presenter and the moderators are muted. For most lectures, including this one, Randy Strobel is the host, and he, Dave Wilhelm, and I are moderators. As always, thanks, Randy, for setting up these Zoom webinars. The Zoom platform offers a number of means for interaction that we use. We'd like to handle most questions at the end. To enter a question at any time during the lecture, click the Q&A icon, type in your question. You need not wait until the end. For those few persons joining by phone, we will unmute you at the end in case you have questions. We might also unmute other questioners if they need to clarify their question. If you have a quick question for which you'd like an immediate answer, click the raise hand icon and enter the question. For these, the moderators will use their judgment about interrupting the presenter during the presentation. Also use raise hand to report any technical issue you might experience. There's also a chat option that allows you to type a message for all participants to see. Feel free to use that before the lecture starts to greet others. Be sure to use the all panelists and attendees option. I'll mention 3 other ways we use chat shortly. Many of these GSM webinars, including this one, are recorded and will be made available on YouTube. We will send members and other participants an email with the link when the recording becomes available. The full lecture schedule is on our website, gsm.org. Thanks to Steve Erickson for arranging another outstanding slate of topics and presenters. As with our live lectures, this lecture is free and open to the public, not just GSM members. If you're not a member, please open the chat box and type non-member in your city and state, province, or country. Also mention how you found out about us. We like to see how many non-members attend so we can see how well our information reaches the general public. So please do that courtesy for us. Thank you. Of course, we would love for you to consider joining our organization. Membership information and forms are on our website. Membership dues are the primary method by which we fund these lectures and our other programs. Also, we can count the number of devices that tune in, but not the number of people watching from each. So we can get a better count of those participating. If you're watching with at least one other person, type 2 persons or whatever your number is in the chat box. Thank you. Continuing education credits. These lectures are eligible for 1 hour of CE credits. If that's something you can use chat to request a form, include your name and email address. If you don't want everyone to see this information, there is a chat option that allows only the moderators to see what you type. Following the meeting, we'll fill out a form, sign it, and mail it to you. Let's see, any other announcements?
Are you going to talk about State Fair?
Yep. The State Fair will be held in the state of Minnesota this year. GSM has a booth, and our VP, Patrick Funstein, will be coordinating our efforts in that regard. There may be more information coming out on this later. Let's see. Tonight's speaker, Cameron Davidson, earned a BS in geology from the University of Wisconsin-Madison in 1986 and received his MS and Ph.D. from Princeton University in 1991. He spent 3 years as a postdoc at the University of Basel in Switzerland before moving to Beloit College, where he taught for 7 years before joining the Carleton Geology Department in 2002. Professor Davidson has worked in Alaska for over 30 years, and his current research is focused on the accretion and translation history of Southern Alaska using a uranium-lead geochronology and hafnium isotope geochemistry of detrital zircon. Wow, I got that out. Cameron, welcome. We're looking forward to this.
Thanks, Joe. Really appreciate that. It's really a pleasure to be here. I've always enjoyed giving these lectures, and it's kind of sad we're not in person, but this works remarkably well, as we were talking about before. So when I was putting this talk together, I ended up with a little over 100 slides. I pared it down to 95. But there are some places that I can cut out if we're running too long. So, but some of the slides are very quick, so I should be able to do it within the hour, let's hope. So let me go ahead and share my screen. And I can start right. So really, this talk is broken up into two talks or two halves. The first half, I thought what I'd do is do a little bit of review about how we go about dating rocks. And a lot of this, I'm sure, will be review for many of you guys. But I thought it's kind of fun, and it's similar things I do in my classes. And then the second half is specifically applying some of the more modern techniques to what we're doing up in Alaska these days, and really coming up with some pretty surprising, that is rapid, geologic rates. That are within really the resolution of our ability to date them. So that's the plan. Oh, and also if people want to interrupt, that's fine. Once I get going, it's often hard for me to see raised hands, but if I guess the moderators look at that. If they want to interrupt me, that's fine. Right, so really an age-old question, I think, that humans probably ever since we've been able to think have probably asked is, how old is the Earth? And we know now, at least our best estimate now is about 4.5 billion years, or 45-67 million years. And I'll be talking a lot about million years, or MA, in this talk. And the reason we know that is by dating meteorites. And the assumption here, of course, is that the meteorites formed about the same time as our solar system formed. And so by dating those, and sure enough, they keep giving the same answer when we date these things. And that gives us an age of the Earth pretty well constrained now to about 4.567, depending on when you decide what is the age of the Earth. And that's a whole nother discussion. Now, if you look at the geological time scale, and this is the most recent one published by Geological Society of America, and you look at the main time scales, or the main units here, or divisions, I should say, Cenozoic, Mesozoic, Paleozoic, etc. Something jumps out at you, presumably, and especially if you look at, let's pull apart the word. So let's pull apart Paleozoic. You see zoic there, and that's the same root as zoology. And so it clearly has something to do with life. And paleo, of course, is old or ancient. So ancient life is how you would translate that, right? And Mesozoic would be middle life, and Cenozoic would be recent life. So clearly the way this thing is organized is around life. And in this case, it's life in the rock record, that is the fossil record. And so we'll come back to that. But of course, if you look at the geologic time scale at a scale, so those last ones were not to scale, but here's one to scale, then those three most recent eras, the Paleozoic, Mesozoic, and Cenozoic, you can see really only occupy, the first 500 million years. And we've got the rest of geologic time. And when you consider the Precambrian, there's not much in the way of fossils there. And that's why the Phanerozoic has been expanded so much, because we have a really good fossil record there, where it's less so in the past. And that's why, you typically see that expanded. And again, this is to scale, unlike that last diagram I showed you. And you can see the Paleozoic is much longer than the Cenozoic, for example. And I'll get to this in just a little bit, but one of the things is, for a long time, we didn't know what the left-hand column here was, where you see that calibrated time scale in millions of years. When this time scale is worked out, the absolute age of these rocks was really poorly constrained. That's a relatively recent phenomenon. So how do people do it? Well, I just wanted to review, and again, this is going to be a review for many of you, is talk about the difference between relative and absolute dating. And really relative dating is what we do all the time as geologists in the field. When you see things like this, where you see this beautiful basalt dike cutting these flatline sedimentary rocks, well, clearly the sedimentary rocks had to have been there before the dike cut them. So the sedimentary rocks are older than the dike. And that's just a basic example of relative age dating. And so I just wanted to review some of the relative dating techniques we use, and some of these are sort of stating the obvious clearly, like this first one, which is the principle of superposition. And of course, if you see some flatline sedimentary rocks, then the rocks on top have to be younger than the rocks on the bottom, sort of, again, stating the obvious clearly. And of course, this assumes the principle of original horizontality. That is, most sediments in nature are laid down horizontally, okay? And as long as nothing has happened to them, like been tilted up during a mountain building event, then the rocks on top must be younger than the rocks on the bottom. Well, when this isn't the case, that is when rocks have been tilted up vertical or been folded, often it's hard to know which way is the younging direction just looking at the rocks. So you need something else, and you need things like ripple marks or graded bedding, cross bedding, or mud cracks. These sorts of things let us know what the younging direction is, and that figure on the right, or the picture on the right, is from Zion National Park. Beautiful cross-bedded sandstones, and in this case, these rocks they've been tilted a little bit, but they're right side up based on those sort of sedimentary structures. Perhaps one of the most important things that was used for building that geologic time scale was correlation. And this was really pioneered by a guy named William Smith back in the 18th century. He was a road engineer in the UK. And what he noted was that rock types and their characteristic fossils can be correlated over really large distances. And on top of that, what he noticed was that the fossil assemblages are always found in the same order. That is, from old to young. And of course, today we know that as the principle of faunal succession. And this is exactly what Darwin used, right, when he built up his case for evolution. And it was from the rock record. So going back to our time scale, again, that's why we see Cenozoic, Mesozoic, and Paleozoic. It was all built around the fossil record. And the reason why we go from, say, the Paleozoic to Mesozoic was that there was a big extinction event at the end of the Paleozoic. In fact, that's the largest one, the end of the Permian extinction. And that's why they saw this change in the fossil assemblages. They went, whoa, there's something big happened. And now in the Triassic, the fossils look at first not very abundant, and then totally different than what we see in the Paleozoic. And in fact, many of these period boundaries are also between, say, Devonian and Carboniferous and Permian, et cetera, are also extinction events. And that's why the new name. Right. So another thing, and I'd be remiss if I didn't mention this, another thing about William Smith, fascinating person, is that he was the first one that's widely recognized as making the first geologic map, especially on a regional scale. He made a geologic map of the entire UK. And if you're interested in more about that story, this is a great book by Simon Winchester, The Map That Changed the World. Some of you probably already read this. It's read this. It's a really, really great book, and it tells that whole story. Okay, a few more. Principle of cross-cutting relationships. We also use this all the time. That was like that example I gave right at the beginning of dikes cutting sedimentary rocks or any kind of rocks. Also, of course, if you have faults, those have to be younger than the rocks they cut. Unconformities are also important in working out relative dating. And perhaps the most dramatic of these are angular unconformities, where you see, say, a bunch of sedimentary rocks that were deposited, uplifted, eroded, the whole basin then got subsided again, and then new sediments deposited on top. So here are these, tilted sedimentary rocks, and erosion layer, which we show by these squiggly lines, so that's the unconformity, and then you deposited new sedimentary rocks on top, and of course we call those angular unconformities for obvious reasons. But we also have non-conformities. This is where you have sedimentary rocks put on top of igneous and metamorphic rocks, and again some period of erosion. So this is missing time, right, are these unconformities. Now the probably the hardest ones to spot in the rock record are disconformities. So you might have a stack of sedimentary rocks, And there may be a period of missing time in there, a disconformity. And the only way you might know that is if you know something about the fossil assemblages, right? If you see, oh, wait a minute, there's 50 million years missing here, then you might go, I bet you we have a disconformity in there. Right, perhaps the most famous of these unconformities is Hutton's unconformity, and I had the pleasure of doing my field camp back in the 80s in the UK. And we got to visit Hutton's unconformity. This is a friend of mine, Rudy DeZoten, standing on Hutton's unconformity. And so I'll just point out a few things here. There you can see the bedding off to Rudy's right, which is dipping off to our left, I guess. And below his feet, you can see another bedding orientation, and that bedding is almost vertical. Even though the rocks look remarkably similar in both of those places, but this implies that there has to be an unconformity between those vertical beds and those slightly dipping beds. And it was here back in the early 1800s that John Playfair went with James Hutton, as a matter of fact, and gave this famous quote, "The mind seemed to grow giddy by looking so far back into the abyss of time." I love that. So, back in, 200-300 years ago, people really started to appreciate, by making these detailed, careful observations, like at a place like Hutton's unconformity, that, the Earth has got to be pretty old. The big question, of course, is how old? And this is what we still need to get a handle on. And so this is where absolute dating comes in. And this is, of course, the age of something in years. And how are we doing on time? Yeah, I think I'll have time to do this. So I thought it would be fun to look at some of the early attempts at age dating. And one of the things that people tried was, well, let's do sedimentation rates. And what you would need, of course, is some sort of average sedimentation rate. You would also need to estimate the total amount of sedimentary rocks that have ever been deposited on Earth, which is probably a big task, although I'd love to write that NSF grant and say I have to travel all over the planet and measure strat section. Would you please fund me? And then the solution, if you do this, is about 500 million years when the people attempted this. And this was encouraging because they were like, okay, yes, we're on the right track. The Earth has got to be quite old, based on, of course, this is just very much a back of the envelope calculation. And so what are some of the problems with this method? I'm sure many of you have already thought of these. Well, number one, you've got these unconformities. It's an incomplete record. There's missing time in the rock record. There's also no one place with a continuous record. So you are going to have correlation errors. You might write your friends in Europe and Australia, and they'll send you their local strat section. But then how do you accurately correlate everything could be problematic. And then probably worst of all is that sedimentation rates are highly variable. So almost to the point of making this calculation almost meaningless. But anyway, what do? You try things. Another one that people tried was ocean salinity. This one's kind of clever, I thought, is that the assumption here is that the oceans began as fresh water and became salty thanks to weathering reactions through geologic time. And that's probably a good assumption. So now you have to think about, well, what do we need to do this? And you would need to know the volume of the oceans. Now, back in the 1800s, that was a big question, right? We had a few soundings in places, but there was no understanding of how much volume the oceans had, unlike today, where we know it quite well. You'd need to know the yearly input of water from land, that is via the big rivers on the planet. And then you'd need to know the chemistries of what salts are being brought in by the rivers and what are the oceans in terms of its current chemistry. And when people did this, they got an answer around 100 million years. So that was kind of interesting, sort of same order of magnitude. The main problem with this method, of course, is that we find evaporites, that is big salt deposits in the rock record. And so clearly you're removing salt from the oceans at various times throughout geologic history. And then, of course, one of the more famous calculations was by Lord Kelvin in the early 1900s. And this was using the new thermodynamics that had just been invented in the last century. And so this was physics. Let's apply physics to the problem. And by doing that, they get, and the assumption here, of course, was that the Earth was completely molten when formed. And by looking at the modern heat flow, you can actually do the calculations and say, oh, well, this is how long the Earth has been cooling from being a completely molten mass. And the solution that he got was around 70 million years. And this was, of course, the best solution supposedly at the time. And this is, I love this story because, you know, I always tell my students, this is where if you know something can't be true, then you got to point it out and you got to figure out why. And I love this quote from T.C. Chamberlain, who started the geology department at the University of Chicago. And he said, well, sir, in this particular case, the laws of physics need to be changed. I love that quote. And so the question is, well, what was Lord Kelvin missing? And the answer, of course, is radioactivity. So there actually is another heat source in the Earth. It's just not been cooling from the primordial heat of its formation, which is what the assumption was that Lord Kelvin used. And he didn't know about radioactivity. It was just being invented when he was making these discovered when he was making these calculations. And it was Marie Curie, of course, in 1903, who was the first to isolate radium, a radioactive substance. And then shortly thereafter, people went, oh, wait a minute, this could be incredibly useful for dating rocks. And Lord Rutherford was one of those who pointed that out right away. And then one of my heroes, Arthur Holmes, in 1911 was the first to publish a rigorous uranium lead age of a rock of 390 million years he got for a Devonian granite from Norway. So off we go. This was, you know, we've been doing it for about 100 years. We've gotten really good at it recently, but it's a relatively recent thing of getting, you know, rigorous radiometric dates from rocks. Right, so modern geochronology. It uses radioactive isotopes to date rocks. So let's just go through that really quick. Here's an example system where uranium-238 goes to lead-206. And that arrow turns out to be many steps. And I'll show you those in just a second. But I just want to get some terminology out of the way. The uranium atom we call the parent atom. The lead atom is the daughter atom. And there are two common types of decay. Radioactive decay. One is alpha decay, and this is where you release 2 protons and 2 neutrons. That is, you're spitting out a helium nucleus from the nucleus of, say, the uranium atom. And these things, we call them alpha particles. And again, it's a helium nucleus. The other type of decay is beta decay, and this is the release of an electron from the nucleus. And you may say, well, wait a minute, that doesn't make any sense. Electrons are a cloud around the nucleus. But this is a reaction that happens in the nuclei of radioactive minerals. And this is where a neutron spontaneously decays to a proton plus an electron. And of course, the electron says, I'm in the nucleus, and gets ejected out of the nucleus because it doesn't want to be there. And that's called a beta decay. And those electrons are called beta particles. So those are the 2 most common types of decay. And so here is an example using uranium-238. So uranium-238 will spit out a helium nucleus, and it'll go to thorium. It'll spit out a beta particle, and it'll go to protactinium, etc. And a nice way to see this is on this type of diagram. So this is atomic number, that is the number of protons on the y-axis over here. And on the x-axis is the number of neutrons. And so way over here on the right, you can see uranium-238, and notice that's got 92 protons. That's what defines it as being uranium, and 146 neutrons. And an arrow that's oriented like this, going from uranium to thorium, that's an alpha decay, right? You lose 2 protons and 2 neutrons, it goes there. And then this is a beta, beta, and then alpha, 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 alpha. And then it's a branch decay where you have some that go beta, some that go alpha, etc. And eventually you get down to lead-206. So these are the many steps that I was referring to before. Let's see. Oh, why isn't it advancing? There we go. Okay, So dating, how does this actually work? Well, let's go ahead and let's see how we're doing on time. Yeah, we can do this. Let's let N be the number of parent atoms in our rock or mineral that we're trying to date. dN dt is the rate of change of the number of parent atoms. And so we can write a proportionality to that. So the rate of, or the number of atoms in your rock or mineral is proportional to this rate of change. And we need a minus sign there because we're losing parent atoms with time, right? But of course, you can't really do anything with an equation like that. So we got to turn this proportionality into an equal sign to solve it. And to do that, we need a proportionality constant, or a fudge factor is what it is. And so now we've got an equal sign. And it turns out this proportionality constant, or this fudge factor, actually has physical meaning. It's what we're going to call the decay constant too. Oh yeah, put that there. So it's what we call the decay constant, and it's unique for whatever isotope, or radioactive isotope, that you're talking about. All right, so you take that basic equation, you rearrange it, and you integrate, and you get this. And of course, now you have a constant of integration that you got to deal with. So you can evaluate C, and now you got to know something about your system, or you got to define your boundary conditions. And in this case, we're going to say, okay, let's set time equal to 0. So this is when the clock starts. So let's say you grow a mineral with some radioactive elements in it, and now you start the clock at t equals 0. And of course, at that time, we're going to say the number of parents that's there is the original number of parents. So with those constraints, we can evaluate this equation. So if t is 0, that goes to 0. So therefore, C is just minus log n naught. And now we plug that back into the equation and rearrange, and you get the basic equation of radioactive decay. And so it's a super easy derivation, as you can see, to get to this basic equation, which is kind of handy. And just to remind you what the different parts are here, N naught is the number of parents at t equals 0. That is when the clock starts. N is the number of parents at t at some later time. T is time in millions of years typically. And again, lambda is the decay constant. And again, this depends on whatever isotopic system you're talking about. Another useful concept is the concept of a half-life. And this is, of course, the time required for half of a given number of parents to decay. If you want to say that mathematically, you just write it this way. And so you could plug that into or substitute that into the basic equation. And what you see is the half-life is directly related to this fudge factor, to this proportionality constant, or the decay constant. So to really understand equations, I always need to graph it. It just is an easier way to think about equations, I think. So let's just come up with some fictitious isotope that has a really rapid half-life of 25 years. And we'll plot the number of parent atoms, a ridiculously low number here on the y-axis. And let's say we start off with 100 atoms. And then time is here on the x-axis. So at t equals 0, we got 100 atoms. After one half-life, then we have 50 atoms, of course, because it's been cut in half. And after another half-life of 50 years, now we have 25 atoms, etc. And if you plot that, then you see this nice exponential curve, which is what you better get, because notice we have an exponent in that basic equation. Now, the reason I like to show this, though, is that this is super important when it comes to dating rocks and minerals, because you need to have an isotopic system that you haven't had that many half-lives happen, because if you lose all of your parent atoms, you have nothing left to measure, or the amounts are so small that you can't measure it anymore. So you need to have pretty long half-lives to go and measure rocks, most rocks anyway. Right, so let's go back to our basic equation. And one of the things that you might have been asking yourself is, well, wait a minute. If n naught is the number of parents at t equals 0, there's no way we can know that. I mean, we weren't there 200 million years ago when this rock first formed. And since then, we've been losing parents. So clearly, we can't use this equation to solve for ages of rocks. And what you have to do is use the age equation. So this is another derivation. I'm not going to go through it. Takes a little bit longer, but not much longer. But now we've replaced that N naught with some other terms that are D, and this has to do with the daughter atoms. So let's go ahead and look at those. So D naught in this equation is the number of daughters at T equals 0. And you may say, well, wait a minute, we just replaced N naught with D naught, and how do we know how many daughters were there at the time of this thing first formed, say 200 million years ago? Well, this is where it depends on your system. So this is where the mineral zircon, a lot of geochronologists say zircon is sort of God's gift to geochronology, because zircon is one of these minerals that accepts uranium when it grows, but it excludes lead. That is, it excludes the daughters. So when that thing crystallizes and say 200 million years later, you measure the amount of lead in it, most, if not all of that lead came from the decay of the uranium. And there wasn't any lead or very little lead, it turns out, that was there when the thing formed. And so D in this equation is the present day number of daughters, so that we can measure, no problem. And the rest of these you already know, present day number of parents. So those first 4 we can actually measure, or in the case of D naught, we can ignore, or we can estimate it. There are ways to estimate this too. And we can solve for time. So what we use is the age equation, not the basic equation for dating rocks, not the basic equation of radioactive decay. So dates versus ages. So you may say, well, wait a minute, aren't those the same thing? Well, they're not, it turns out. A date is the number one obtains from solving the age equation, whereas an age is the interpretation of that date equals the age of the rock or mineral. Okay, so this is where a human has to get involved and say, all right, I got this date, does it mean anything? And so for a date to equal the age of a rock or mineral, we need these next things to be true. The parent and daughter measurements are accurate and representative. And that, you know, if you're a good geologist, a good geochemist, hopefully you can do that well. The decay constant has to be known. We know those pretty well. They're constantly getting tweaked, but they're not going to change much now. We know them quite well. D naught is known. This is one of the things that you have to know is either know D naught or estimate it or ignore it. So in the case of zircon, usually it's so small you can either ignore it. We have ways of actually trying to estimate it to get a more precise date. And then finally, the rock or mineral did not gain or lose parents and or daughters since it formed. Now, this is the tricky one. Another way to say that is that it has to remain a closed system since that thing formed. And sometimes that doesn't happen, all right? So let's look at, and I'll come back to that, it turns out. That turns out to be an important part of the story up in Alaska as well. So let's look at some example isotopic systems. The uranium lead system is a real workhorse for geochronology. And one of the reasons is because it turns out we have 2 clocks in there. We have the 238 to 206 clock and the 235 to 207 clock. And this is one of these ways we can test for a closed system, it turns out. If you solve for both of those chronometers and they give you the same answer, what that's telling you is that your system remained closed since that rock formed. So it's a great internal check. And oh, I should have pointed out, those are the half-lives over on the right-hand side there. And I always think it's kind of, you know, an interesting coincidence that the half-life of the 238-206 chronometer is about the same age as the Earth. It's kind of neat. Another one that's commonly used today is potassium 40 going to argon 40, and this one is a real workhorse as well, especially for thermochronology, it's called it, but I don't have really time to go in that, but it also gives very good dates. Rubidium strontium is kind of a little bit of a different beast, and that's why I wanted to bring it up. You don't use this really to date rocks at all. What you use it for are called isotopic tracers. And because it's has such a long half-life, you can see that they're 47 billion years, longer than the age of the universe. The change in that ratio of rubidium to strontium is so slow that actually gives you useful information if you measure that ratio in ancient rocks, for example. But again, that's another talk. And then finally, just because everyone, when they find out you do geochronology, they say, oh, so you use carbon dating. And actually the answer is no, we don't use carbon dating, at least most geologists don't. Archaeologists do, or people who are interested in recent things do. And the reason for that is because the half-life is quite short for carbon-14. It's only 5,000 years approximately, and this means the maximum age you can measure is about 60,000 years. And this is because of that exponential decay, remember, of radioactive elements. You just have had too many half-lives pass. If you get much older, and really pushing 60,000 years is pushing it, you just get meaningless numbers. All right, so let's go back to the age equation, and now let's apply it using uranium lead. That's the one that I'll be focusing on. And you can assume that this daughter is more or less zero or small, and we measure these two things. And so now the question is, how do we go about measuring them? And the way we measure them is with mass spectrometry. And what you do, and this is a very simplified diagram of how a mass spectrometer works. You have some sort of source, so you put your mineral grain here. These days, we typically blast it with a laser that ionizes it. You take that ion beam and you run it down a tube in through a magnet, and you make it go through a 90-degree bend or some angle. And the heavier atoms, because of momentum, aren't going to be able to bend as much as the lighter atoms. And so this does mass discrimination. And all you need now are some detectors down here, which counts the number of atoms of different masses. And we've gotten so good at controlling these ion beams now that we can measure easily the difference between one neutron, and quite accurately. It's remarkable how well these things work these days. And this is why we made such, really in the last 15 years, it's just been remarkable, the progress that people have made in getting super accurate data. Right, so where we go, where I take my students, is the Arizona Laserchron Laserchron Center down at University of Arizona. It's one of the state-of-the-art facilities on the planet, actually. And this is one of the mass spectrometers that we use down there. On the left here is the laser system. That's where you put your samples in. Here's the flight path that goes through one magnet, another magnet, and then here's the detector tree over here. Here are some of my students dating zircons. They've got some zircons up on their screen, and they've got the laser beam right there on that one in the middle, and getting a date. So how does this work? So here's a scanning electron microscope image of a zircon, and this is after it's been analyzed. And in this case, they took 3 separate analyses here. And what you see here is a pit where the laser was, and you just blast a very shallow hole there that liberates enough material where you can get a date. So in this case, that hole might have given you 73.1 plus or minus 0.9 million years, for example. And why is this really helpful these days is that by using, and I should have pointed out that these pit sizes, these are actually quite big. Nowadays, we can get good ages down to 10 micron diameter pits. We typically use 20 micron pits now, but you can do it as low as 10. And what this allows you to do is look at, like, say, complex zircons like this. So here's another one of these electron microscope images of a zircon. This is about maybe 400 microns across. And you can see, the zircon grew, and you see these like nice growth zoning, almost look like tree rings. And by putting the laser there and over here, you see it looks a little bit different. And then you have this younger rim around it, and you can work out those ages. So in this case, George Garrels and others showed that this core was about 130 million years. And then this zircon got caught up in a pluton and an igneous rock at 96 million years and grew some new zircon. And then the whole thing was metamorphosed again at very high grade conditions at 57 million years. So you can start to pull together some really detailed histories of the rocks that you're studying, thanks to the ability to go small, really, with these dates. All right, so I think, we're now in the second half of my talk, and I'll try to keep it to 20 minutes or so, so we don't run late. So now what I'd like to do is show this example from Alaska, and I want to acknowledge John Garver from Union College. We've been working together on Alaska rocks for the last 10 years now, and it's really been a great partnership. So I just want to acknowledge him, plus a ton of students. We've had maybe 30, I think over 40 students that we brought up there over the last 10 years. This is the last place that we got to do field work in 2019. This is Harlequin Lake up in Alaska, and right before the pandemic happened. And then of course we couldn't go last year, and we can't go again this year, unfortunately. But next summer, it looks like we'll be able to go back up. But this is a beautiful place. The main takeaway for this section is that sedimentation, burial, and intrusion of igneous rocks can happen over short periods of geologic time. That is in less than 1 million years. And so the area we've been focusing on is the southern part of Alaska, all the way over here in the west at Sanik Island down to Baranof Island, and pretty much the whole southern margin of that area. And the area that we're working on, or the group of rocks we're working on, is called the Chugach-Prince William Terrane. So here's a tectonic map of that area. Again, here's Sanik Island there. Here's Baranof Island here. Here's Seattle to get you oriented, and Anchorage is right there. And all the rocks in green are the rocks of this Chugach-Prince William Terrane. And what's remarkable here is that I could land you out here on the Shumagon Islands or on Sanak Island and show you these rocks, and you would say, whoa, those look exactly the same as the rocks in Prince William Sound or Kodiak Island or Sitka. It's remarkable how uniform these rocks are all along the margin. These are all the places that we've been over the last 10 years. And the last hole we have to fill is this area right around Glacier Bay. That's where we're planning to go next. So what is the Chugach-Prince William Terrane? Well, it's a late Cretaceous to early Paleogene or Paleocene accretionary wedge complex. And so here's a cartoon of where those rocks were probably deposited. It was along some continental arc system. So you had subduction of oceanic lithosphere, and any sediments that were being delivered out into the ocean basin are then scraped off and incorporated into this accretionary wedge, or this accretionary prism. So we think this is the geologic setting for the formation of these rocks. And this will become important in just a little bit on getting dates for these rocks. So just to show you what this looks like on the ground, here is a geologic map of the sort of the core of the Chugach-Prince William Terrane. Here's Anchorage to get you oriented. And all of the rocks south of that red line that I just put up there, that red dashed line, are the rocks of the Chugach-Prince William Terrane. And that red line is the Border Ranges Fault. So this is a terrain bounding fault that separates the rest of North America and Alaska from this accretionary wedge complex, which has now been plastered onto the Alaska margin. Just to give you a feeling for the geometry of this, I'm going to show you a cross section, AA prime right here. So here's going from AA prime. Here's the Border Ranges Fault right there. All of these rocks are the Chugach-Prince William Terrane. And in this area where it's quite thick, it's broken up into two groups, the Valdez group and the Orca group. And we've been doing lots of dating, and we're getting depositional ages of these rocks starting in the late Cretaceous all the way into the Eocene, actually. And you can see they systematically young as they go from inboard to outboard, although actually this story is getting more complicated, it turns out. But in general, the Valdez group is older than the Orca group. Now, the other interesting and curious thing about this particular accretionary wedge complex is that you see these red blobs, and these red blobs are igneous rocks or plutons that got intruded into this accretionary wedge. Well, that's weird. I mean, if this was sort of a modern arc, and actually it is part of a modern arc now, here's where the modern volcanoes are in this configuration. You would expect the plutonism to be over here, not out here in what we call the forearc, that is out in front of the modern volcanic arc. So one of the outstanding questions has always been, well, what the heck are these plutons doing in this accretionary wedge complex? They shouldn't be there. And I'll come back to that. So let's just look at the sedimentary rocks first of the accretionary wedge. They're beautiful turbidites. They're interbedded sands and shales. The shales here are black. The sandstones are more gray color. And you can see some of these are quite thick. Some of these are, 5 meters thick. And these things are singular events. It was either like an earthquake or a big storm, and these things come down as these big turbidity flows and get deposited essentially geologically instantaneously. And then when things quiet down is when you get the shale deposition. So you can see you've had these sort of these big, sandstone, just one after another. And this stack of rocks may only be 1,000 years represented there. We don't really know. But one of the things we're appreciating is that probably it didn't take that long geologically to accumulate a lot of these rocks. Here's an example of one of the bases of these sandstone beds, just beautiful fluke casts, which gives you direction of flow and things like that. Right, if you go to, and that was way out on the Shubingen Islands out to the west. This is in the Prince Rupert area, and very similar looking rocks. And what we do is we land here and we grab one of these sandstone bodies, like right there, and we grind up the rocks and we separate out the zircons, and then we mount them in one of these 1-inch epoxy rounds. And that's what, this is a photomicrograph of one of these things, not the same one, but a similar one. And so what we do is we have a field of zircons, okay? And then we surround them by these different standards, because you need to standardize your mass spectrometer, and then you go after the unknowns. And what you do is go in and analyze these detrital zircons. They're called detrital zircons because they're detritus. They're the sand particles that came down from the surrounding mountains and deposited in this sandstone. And nowadays we're getting 300 plus analyses, and it looks like now they're going to 600 analyses per sample. Every year we do more and more analyses because it's just getting faster and better and cheaper, it turns out. But most of our, at least recently, most of our samples have been 300 analyses. So you go in and you analyze 300 of these things, and you may ask yourself, well, why are you doing this? And let me give you a modern example of why it's helpful. So here is a geologic map for the area right around Anchorage. So there's Anchorage right there. And what it gives you is information about what's called the sedimentary provenance. So on this geologic map, all these different colors, of course, are different age and different types of rocks and different ages of rocks that have zircons in them of different ages. And you can see we have some major river systems here, like the Susitna River and the Kinnick River, et cetera. And this is Cook Inlet down here. And these rivers are all contributing zircons from all of these different age rocks, and they're currently getting deposited down here in the ocean in Cook Inlet. So if you were to go there today and say, select a sandstone from there that just got deposited and analyze all the zircons, you would expect a whole range of different ages. And it kind of gives you a fingerprint of what types of rocks were actually exposed at the surface when that rock was deposited. So again, that's called sedimentary provenance, which can be super helpful in figuring out tectonic histories of blocks. So here's an example of one of the ones we dated, and this is from a 50 million year old rock. So this rock was deposited 50 million years ago or 55 million years ago in the accretionary wedge complex from Yakutat, Alaska. And so this is a histogram of over 300 zircons that we dated. And so on the y-axis is the number of zircons, on the x-axis is age in millions of years. Notice we had to change the scale here because this is the Precambrian, this is the Phanerozoic, and you see a wide range of ages. We even get some Precambrian ages. But the majority, and this is true of most of the CPW, the majority of zircons are pretty young, mostly Cenozoic and, well, mostly Mesozoic with some verging into the Cenozoic. And another way to look at these data is you fit a probability distribution function to the data, and then you can start pulling off the ages of these peaks. So there's a big peak of zircons at 72 million years, 155, et cetera. Right, so what can we learn from dating detrital zircons? Well, sedimentary provenance, like I just showed you, what was at the surface when these rocks were being deposited. Another thing you can get is the actual depositional age of these rocks. And it turns out to be a maximum depositional age. And what do I mean by that? Well, here's an example from our backyard. So here's the St. Peter sandstone right in St. Paul. And if you're to zoom in on the St. Peter sandstone, of course, it's made up of these beautiful rounded quartz crystals, quartz grains. But turns out to be a lot of zircon in here as well, it turns out. But clearly, this is a maximum depositional age if we were to measure the zircons in there, because these rocks, the St. Peter sandstone, they have to be younger or the same age as the minerals they contain, right? So if you get a 300 million-year-old zircon out of this, then you would have a Nature paper, because what you may or may not know about the St. Peter sandstone, it's got to be Ordovician in age, because overlying the St. Peter sandstone is this Platteville formation, which is a limestone, and this has beautiful fossils in it. And all the paleontologists would tell you those are classic Ordovician fossils. So we know these rocks are about 450 or 480 million years. But it turns out that in a lot of sedimentary environments, you don't have these interbedded fossiliferous layers. And so you really have very poor fossil preservation, or they just don't exist at all. And so you need another way to get the age of deposition. And this is where zircons come in. So let's look at the depositional age in accretionary prisms. Well, here's this accretionary prism. And if you're in an active arc, then you would expect zircons forming today being shed into that basin. And so the nice thing about maximum depositional ages in these active accretionary prisms near an arc is that they're probably pretty close to the actual deposition ages of the rock, which is super handy. Okay, I got to speed up here because I see we're only got 10 minutes left. Okay. Right, so maximum depositional age. Well, here's that same sample I just showed you, and you look at that and you're saying, okay, well, what do I choose? I've got a whole bunch of ages here. And there's a bunch of different ways people have approached this question or this problem. You could take, the obvious one is take the youngest single grain, right? So you say, all right, I look here at my histogram, I've got about 20 zircons that are between 50 and 100 million years. So let me just take the youngest one of those, and my rocks must be that age or younger. Or older, I mean, sorry. Or you could take the youngest 3 zircons within air. And you'll see why this can be handy, because sometimes this youngest single grain may not give a good age because of these rules we talked about before. It may have not been a closed system. But if you take the youngest 3 and they're all within air, then that's probably a pretty good maximum depositional age. Another way you can do it is take the youngest statistical population. So this is where you take those youngest 3 and you keep adding zircons until the variation in ages that make up that mean are what you would expect based on the errors that you measure. And the statistical test for this is what's called the mean squared weighted deviation, or MSWD. And if that equals 1, then you know that the variation in those ages is what you would expect if you just have random variations in your analytical precision. The last way that people do this is using the youngest graphical peak. So they say, well, wait a minute, my youngest peak is 72 million years, so that must be the maximum depositional age. And this is a super conservative method. So let's apply it to this particular sample. So here's the top, or the youngest 10 zircons from this particular sample. And so if we apply the youngest single grain, then of course the maximum depositional age would be 52.8 million years. If you apply the Y3Z method, then you would get 53.2. If you applied this youngest statistical population, it would be a little bit older at about 56 million years, but notice you're adding together 11 zircons. And of course the YPP in this case, I would argue, is ridiculous because that peak, that 72 million years, is more than half the sample of the zircons make up that peak. So for this particular geologic environment, that last one is probably a silly choice. But these are the games that people argue about and play all the time. So why all the hand wringing? Well, the reason for this is because of the potential for lead loss. And so if we look at a uranium lead system, if you start to lose daughter product at some point after this mineral formed, then, and that we'd call, say, lead loss, which is not uncommon, it can happen. They actually make zircons look younger than they are, right? If you lose some of the daughter after it formed, you calculate that ratio, you say, oh, this thing is 50 million years when it really should be 100 million years. And here's a schematic showing why that might happen. So if you grow a zircon and you incorporate a certain amount of uranium in it, when that zircon first grows, it's got a nice crystal structure. It's this nice container for the uranium, and then you start making lead. But with time, especially with high uranium zircons, with time, you can start, thanks to the radioactive decay of the uranium in there, you're literally starting to rip apart the crystal structure of the zircon crystal. And it starts to break down, and it even can become a glass. And if that happens, now that zircon can react. If you have some chemically active fluids that move through your rocks, you can start leaching lead from your system. So you can get lead loss. And that's one of the things you got to be careful with. And so for this particular study, we don't use the youngest single grain because of the potential for lead loss. But if we look at the first youngest grain and they're all within air, then we add those together, and that's our maximum depositional age. And this is what a lot of people are settling on. They're either doing Y3Z or YSP. All right, good. All right, so let's apply it to the rocks up in Alaska. I don't expect you to read all these numbers, but all those numbers are the maximum depositional ages for the Chugach Prince William terrain, at least around the area of Prince William Sound. Here's Anchorage over here. And the takeaway point here is that this whack of rocks, which is over 3 million cubic kilometers of material, was deposited in over a relatively short period of time, about 9 million years, between 60 and 51 million years ago. And now what I'd like to do is turn our attention to the plutons that intrude those rocks. And so these are the red blobs on here, and these are the Sanic Baronoff plutons, are called, that intrude into the Chugach Prince William terrain. And so let's take a quick look at those, although I see I'm running behind on time, so I'll quickly go through these. And so this is what the plutons look like, beautiful rocks, and we pull the zircons out of those, and we
if we go over a couple of minutes, that's not a big deal.
Okay, so I don't have to race, okay. I think I can finish in about 9 minutes is what I hope. So here's the zircons that we pull out of that pluton, and we usually date around 35 of these things, and if they all give the same age, then we're pretty confident of that age. And in this case, 54 million years for this particular pluton that we dated. And so we did that all on the margin for the various plutons, which again are shown as these red blobs. And one of the things that jumps out at you probably is that notice they systematically young as you go from west to east. So 63 million years in the west to 50, as young as 47. It's a little more complicated over in the east here, but in general, there's this time transgressive nature of these plutons. So any tectonic model for the Chugach Prince William terrain has to explain, number one, well, why the heck is the accretionary wedge being intruded by plutons in the first place? And number two, why do the plutons young from west to east? And so what I'm going to do is I'm just going to walk you from west to east pretty quickly and show you some of the relationships that we see there. So here's far to the west. Here, the MDA for these samples are around 70 to 73 million years, and they're intruded by plutons that are about 10 million years younger. I'm not going to take time to talk about these because I'm running out of time. They're not super important, just some beautiful xenocrysts that you actually find in these rocks. That was just an aside. So now we go a little bit further to the east, or in the area around Seward. And here we find MDAs, again, a pretty big range actually in this area. We find Cretaceous MDAs around 67 million years, but also some Paleocene ages of 56 million years. And what's interesting is that when you look at the plutons that intrude these rocks, some of these plutons are the same age as the maximum depositional age. So within air, notice that these plutons intrude rocks. And in fact, this Hive Island pluton is right next to this sample that we measured, and they give the exact same age. So it was like, huh, well, that's kind of interesting. You're actually depositing sediments in this basin and intruding them by plutons at the exact same time. So that started to get our attention when we first started getting these dates. And again, some beautiful reaction textures with xenocrysts in these rocks, but I don't have time to talk about those. That's kind of another story. So now let's go further to the east still. And same story, we have now slightly younger MDAs, around 60 million years, and intruded by plutons that are pretty close in age. And in fact, in this area, if you go further outboard, so like this first one here, this sample, CV1410, which is 56, was collected right adjacent to this pluton. But if you go further out here on Hinchinbrook Island, we see that sediments were deposited after the intrusion of this pluton. So clearly this is an active sedimentary basin that is still subsiding and being intruded by plutons at the same time. Now this is perhaps the most stunning result, was in the Yakutat area. And here we have what's called the Schist of Nunatak Fjord, which is again the Chugach Prince William terrain rocks intruded by plutons. And there we got 53 million year old for the MDA of those sedimentary rocks. They're now metamorphic, and they're intruded by plutons that again are within air the same age. And what's really cool about this spot is that we, adjacent to one of these plutons, we have this beautiful metamorphic, contact metamorphic assemblage that formed in the sandstone. And this is a garnet starlite schist now, and there's the mineral assemblage. And I'm a metamorphic petrologist in my former life. So when I see rocks like this, I get all excited and say, hey, well, we can do something with those. And you can actually calculate the pressure and temperature at which that rock was metamorphosed. And what we were really interested in, at what depth did that metamorphism happen? And it turns out those rocks got buried to 30 kilometers depth when it was intruded by the pluton. So remember, these were the same age. We got a pluton that's 53 million years old. We have, or 54 million years old. We have a sediment that's 54 million years old. So this sediment was deposited, buried to 30 kilometers, and intruded by a pluton nearly geologically instantaneously. So that implies these rocks were buried rapidly to 30 kilometers, probably in less than a million years, which is remarkable. Okay, and now just to be complete, we'll go all the way to the west or to the east and near Sitka. And the story is not as dramatic here, but we get, you know, a range of MDAs. And again, the plutons in this area actually range in a bunch of ages, 47 to 53 million years. So just to summarize what you saw, this is from west to east, about 10 million year old time difference in the Prince William Sound area. We have plutons coming in during deposition. We also see the same thing in the Yakutat, but here we had control that these rocks, at least in this area, got pretty deep before they were intruded, or buried pretty deep before they were intruded by plutons. And then finally, Baranoff, again, it looks like to be a separation. So this is a whole nother story on why we do think there might be some younger rocks. We just haven't found them yet. That's actually one of the reasons for going back into that area next year. All right, so yeah, let's not talk about these at all. These are different models for this formation of these plutons. And sort of the reigning model is number 4, which is that these rocks, so the question is, how do you get plutons into the accretionary wedge? And one way to do that is you subduct a spreading center, that is subduct a mid-ocean ridge. So that's shown here schematically in this cartoon, where here's the ridge being subducted, and then that gives you a good heat source for partial melting, bringing in mantle melts, underplating the crust and melting that accretionary wedge, forming these nice plutons. And so the question is, well, where does this happen? Yeah, I'm running out of time. This really isn't super important. So here's our model for what this might have looked like when the Chugach Prince William terrain was being formed, where here's the oceanic lithosphere being subducted underneath our accretionary wedge complex. And we would argue that you must have some sort of marginal basin that was actually extending, and this gives you the accommodation space for all the sediment that was being dumped in here. So this gives you the ability to deposit sediments rapidly. But then you must have tectonic thickening going on too to bury them even deeper. This also gives you a heat source by subducting this mid-ocean ridge, bringing up mantle right below this, driving partial melting, etc. And there's actually a ton of geological evidence for this, which we talk about in this paper that we just published 3 years ago now, I guess. Anyway, so where do we think this happened? This is where we are today on the left. But we would argue that you have to slide all of this material back down towards Seattle. And it was probably right off of Seattle. That's a whole nother talk on why we think we can make these links, especially with Yakutat back here in the Seattle area. And that's where we think this stuff is happening. And, again, between 60 and 50 million years is when all the action was. So here's sort of a snapshot of between 55 and 57 million years. But again, that's a whole nother talk. The main takeaway, main takeaway was sedimentation, burial, and intrusion of igneous rocks can happen over short periods of geologic time, at least at the scale of what our errors are in our measurements. And so the next step is to try to apply even higher precision geochronometry to these rocks to see if we can start to resolve that. And that's it. Sorry for speaking a mile a minute, but it caught up to me.
Well, Cam, thank you. That was a fascinating presentation. And it sounds like we've got the material for at least 2 more to come. Is that right?
Yeah, I know. I was just, I didn't know where to stop, but it's all fun.
So, okay. Well, let's see what we've got here in terms of questions. Let's see. First one, how do you measure the half-life, especially the real long ones?
That's a super good question. And I don't know the details, but I know one of our alums, in fact, is one of the gurus now in the potassium argon system. And what she's been trying to do, and she works for the United States Geological Survey now, the USGS, and she's been getting radiogenic potassium because it's not the most abundant isotope of potassium, but been accumulating as much radiogenic potassium and putting it on the shelf essentially, and then measuring literally the amount of alpha and beta decays over, and she's going to try to do this over a 10-year period to try to get that decay constant better calibrated. Most of the early calibrations happened actually as they were leading up for building the bomb. Back in World War II is when the first decay constants started to come out, because they needed to know what these half-lives are and what the activity of the radioactivity was. And so that's from those measurements on how active like a pile of uranium-235 is or a pile of uranium-238 is, they could actually directly calculate this constant by measuring the amount of output of radioactive particles. That's my understanding how they do it. I don't know the details. I know there has been a big push. It's called the Earth Time Effort. And the gurus who run these labs, like the people at Arizona, are involved. One of their goals is to really try to nail down the precision of our decay constants, because right now that's what's holding us back for getting even more precise ages. If we knew our decay constants with better precision, we don't think the absolute number is going to change much, but if we can get the precision of that, the error is small enough, then we can knock down and get down to like 0.1% error or even 0.01% error is what they're going after. So you could start dating things that are like 60 million years plus or minus 1,000 years is what their goal is, which would be remarkable. So I didn't quite answer the question, but and I don't know how they do the long ones. I think it's the same way, but the errors are much bigger.
Okay, and another question from the same person, from Mark. Do all rocks have radioactive materials in them?
Well, that's a really good question. Luckily, zircon tends to be a ubiquitous mineral, at least in crustal rocks. So like in any kind of clastic sediment like sandstones and even shales, you'll find them, they're just tiny. You will find zircon if you can pull it apart properly. In limestones, of course, you typically don't find them, but often in limestones, you find these shaly layers, and in there you will find zircon. So for crustal rocks, it's pretty good. When you get to like oceanic rocks, things that are more mafic, like basalts, it's much harder to find zircon because you need a certain amount of silica to stabilize. Zirconium silicate is what zircon is. But there are other systems. So for example, the potassium argon, there is enough potassium, there's not much potassium in a basalt, but that's what people are using to date oceanic crust, for example, is there's enough potassium in there that they can actually measure quite good now the age of oceanic crust and basaltic crust. There's also a lot of novel systems coming out like rhenium, osmium, and a bunch of, which I didn't put up there. So this day and age, almost anything material you can get your hands on, you can probably extract a date out of, which is pretty exciting. Unless it's pure quartz, then of course you can't.
Mm-hmm. And here's one from Mike. How is zircon extracted from a rock mask?
It takes approximately 3 undergraduate students all week is what it does. No, I shouldn't be. It's not actually that bad. You start off with about 5 kilos of rocks. Say like these rocks, actually all you need is like 2 kilos because there's so much zircon in them. You grind them up. You run it through a Whiffley table, which is a gold table. It's it's just like a fancy gold pan essentially. And luckily zircon is quite dense because it has uranium in it. And so then you take the dense fraction and then you run it through a magnetic separator because it turns out zircon is highly non-magnetic. And then you run it through heavy liquids, which are kind of nasty and toxic. But then once you get it through heavy liquids, you run it again through a magnetic separator. And the last little bit is zircon. And you can get down to like 99% pure zircon after all those steps. And you can push through about 5 rocks in 1 week.
Okay, and here's from Diane Lynch. You said that Nunatak schist has garnets, and wondering if the garnets of the Wrangell area is the same as also, is that also the Nunatak schist?
Oh, great question. Someone who knows the geology in the area. The short answer is no, but it's in very similar tectonic position. The garnets of the Wrangell garnets, which are those famous ones you see in lots of museums, beautiful euhedral almandine garnets. Those rocks are about 90 million years old that they form, and that's when the metamorphism happened, whereas these rocks are about 55 million years. Now, before we started working in there, people correlated the schist of Nunatak Fjord to some of those higher grade metamorphic rocks down in Southeast Alaska. So I can totally see where she's coming from. It's like, whoa, those look similar. But now that we know these dates, the metamorphism is 40 million years separated. So it's a different event, it turns out.
Okay, and let's move on to the chat items. First, well, let's see, there we go.
I don't think there's any questions in there. It's basically attendance information.
Oh, okay.
Oh, okay.
Okay.
Wilhelm, I have a question back from near the beginning of your talk. I think it was Lord Rutherford that did an original dating. They were considered the first dating. Do I have the name right?
Yes, exactly. Well, he was the first one to propose that we could use it to date rocks, and it was Arthur Holmes who did the first rigorous date in 1911.
So I'm just curious how close they got to what we consider the correct values nowadays.
Yeah, and I meant to look that up, and I didn't make the time to do that. My understanding was that it was pretty darn good. Like that granite is still Devonian. And that is, and actually he wrote a whole, Arthur Holmes is an amazing guy. And he wrote an entire book called, I believe it's called The Age of the Earth. And his estimate was like, I forget, his first estimate was like 1.9 billion years old. And of course that blew everyone out of the water. This was like 1912 or 1913 when this published. And then he revised that a little bit later on. I think it was in the 40s, where he said, nope, it's got to be more like over 4 billion years old based on his calculations. So he had it right. And actually, I show another thing is that he was one of the early adopters of plate tectonics. And there's a paper he published in 1943 or 44 that shows how he thinks oceanic crust forms. And you look at that, and it could have come out of a Geology 100 textbook. I mean, it's plate tectonics. It's amazing. I show this in my intro geology courses saying, and we didn't really accept plate tectonics until what, the mid 60s or something. And so he was 20 years ahead of his time in many regards. Just an amazing guy.
Okay, there was one comment in the chat that I thought that you'd like to hear, Cam. And this was put in right near the end. It said, definitely finish and forget the time. This is cool stuff.
Oh, good. I'm glad. I sorry I was speaking so fast, but I get excited about it. It's neat. We're super excited about how fast things appear to be happening. It's just remarkable. Absolutely remarkable.
And remember, you didn't get to start right on the hour either, because Joe did announcements.
That's true. That's true. Yeah.
So,
And I had mentioned that somebody had dialed in, but I don't see that person anymore, so we don't have to worry about he or she asking a question.
well, thank you, Cam, for a wonderful presentation. Thank you to everyone who was listening in. We have a long summer ahead of us. Hopefully we'll see some of you at the fair, or maybe for some field trips this summer. And we'll be starting up our meetings again in September. So have a good one.
Thanks, Joe. Thanks, everybody, for coming.